This morning I had another meeting. I had a lot of problems with my internet connection. So in case I get stuck, it's probably that. But yeah, after a few seconds, it's fine again.
Okay, so let's get started. And so thank you everyone for joining. So today we have Theo Assiotis from Edinburgh. So he's going to talk about some joint moments of characteristic polynomials of random unitary matrices, as you can read. So please, Theo, let's start.
Okay, thank you. Thanks for the invitation. So I'll be talking about these joint moments of characteristic polynomials of random unitary matrices. And this is joint work with John Keating and John Warren, and then with Benjamin, Alper, and Arun. So, okay, let me just start. Oh, I guess let me first put it. Okay. So yeah, so we have unitary matrix U. I'm going to define its characteristic polynomial, well, the usual way. So let's give it this determinant, and we have ei theta 1, ei theta n are the i's of U, and this is the characteristic polynomial. And in fact, I'm going to consider something, something very similar, which is this v. I'm going to put v, which is essentially the characteristic polynomial shifted by a phase so that it's real valued on the unit circle. And then you can see that the absolute value of v is the same as the absolute value of z. And what I'm interested in is these things that are f and as h, which I call the joint moments. So I'm taking the absolute value of this v, which is the same as the one of the characteristic polynomial, at 0, and I raise it to the some power 2s minus 2h, and then I'm also doing that with the derivative at 0 of v, and I'm raising that. So I'm taking absolute value, I'm raising that to the power 2h. I'm taking expectation with respect to the normalized Haar measure on un.
Sorry,
and
again, what is v?
V is this characteristic polynomial shifted by this phase, so it's real value.
Oh, okay, thank you, sir.
And then I have two parameters s and h, and I need these restrictions on h so that this is actually finite. And then so Chris Hughes in 2001 was studying these quantities. I'm gonna give you some more motivation in a moment. I mean, except from the random matrix kind of motivation, there's some number theoretic motivation behind studying this. And then he conjectured that if you divide this by n to the s squared plus 2h and send n to infinity, this goes to some non-trivial limit, which is f as h. And then, I mean, he didn't conjecture an expression for f as h for general s and h. I'll say a bit more about this later. But I mean, he did prove this for interior s and h, but I'll tell you a bit more about the history in a moment. But before that, let me tell you a bit more about some motivation, which is kind of based on this conjectural connection between random matrices and number theory, and in particular the Riemann zeta function. So this connection of random matrix theory and number theory, in particular the zeta function, and essentially begins with the conjecture by Montgomery on this is called the pair correlation conjecture from the 70s, which essentially says that the correlations of the zeros of the Riemann zeta function high up the critical line, essentially these correlations are given by the sign kernel. And then in fact, I mean, in this paper that Montgomery conjectured this, I mean, in fact, he proved the theorem. So if you're looking at the correlations of the zeros, you need some test function. And if that test function, its Fourier transform is supported in some interval, then this actually can be, this is actually a theorem, and that's the theorem he proved. And his conjecture is that this restriction that the Fourier transform, the test function should be supported in a specific interval is actually not needed. So that's his conjecture. And somehow if you have this this restriction for the Fourier transform, then the number theoretic part becomes much, the correlations between the primes, they are much more tractable. While if you don't have that, then it becomes very, very complicated. Okay, so somehow, so you can have this heuristic that zeros of the zeta function behave like, you know, eigenvalues, asymptotic eigenvalues. So you can say then maybe the zeta function itself should behave like the characteristic polynomial. And then, so we have the work of Keating and Snaith in 2000, which they conjecture the following. So they conjecture the following for the moments of the zeta function on the create line, that they should behave as follows. So they behave as log t to the power s squared, and then there's this is the important part. This we have this leading order coefficient. This as is some arithmetic constant, which is not I'm not going to discuss now, but the main thing is that we have this random matrix factor, this fs0, which, if you recall, is the limit of the moments as if you rescale them of the moments of the characteristic polynomial. And so let me tell you what the rigorous results are. So this was proven for s equals 1 by Hardy and Littlewood in 1918, and then by Ingham for s equals 2 in 1926. And other than that, there's no other result which is somehow this strong, but there's a lot of bounds and very extensive numerics which give that this is very consistent. Of course, you might say, okay, I mean, this only matches for 2 values, so this might be a coincidence, but I will tell you, I will say something more in a moment. So it would be very striking for this to be just simply coincidence, and there's nothing, nothing deeper going on behind this. So, okay, and then if you consider some more kind of refined heuristics, so you can approximate the zeta function as a product over its non-trivial zeros and multiplied by product over the primes, and you model this product over the non-trivial zeros as a characteristic polynomial of random matrices. Then in this paper, Hughes and Keating, they use this model, this approximate model of the zeta function, which includes both random matrix, information, and also our arithmetic information, and they showed that this is actually true for that model. Okay, so what about the joint moments? So how do the joint moments appear in this number theory? So we can define Hardy's function, which is given as follows. So essentially it's a zeta function on the Krigman line, and then multiplying this by this gamma function factor. And so this is in some sense the random matrix analog of this V, that this characteristic polynomial shifted by the phase. The thing I'm considering is the random matrix analog of Hardy's function. So again, this is real valued for real t, and then we have that its absolute value, it's exactly the absolute value of this thing, of the zeta function on the critical line. And then work of Hall and the thesis of Chris Hughes, they suggested the following extension of the previous conjecture of Keating and Snaith, which says that if we consider the joint moments, like the moments of this Hardy's function along with its derivative, we have two parameters s and h, right? If we take h is 0, we get back the moments of zeta, right? The absolute value of zeta. This is not there. And then the conjecture is that this should behave like log t to this power s squared plus 2h, which, if you recall, is the same. We had the same power for n, right? When we were looking at the joint moments, we had n to the s squared plus 2h. And then we again have the same arithmetic factor. And then we have this random matrix factor here, which is the limit of the joint moments. So this is what they conjectured. And this is also considered with rigorous results of, let's see, so of Ingham for s equals 1 and h equals 1. And then Conry for s equals 2, h equals 1, h equals 2. So these were known, and they're consistent with the random matrix picture. And then there was a result by Conry and Ghosh in the 80s where they computed this for s equals 1. So 1 and h is 1/2. So it was the only result in number theory that was known where one of these parameters was allowed to be, it didn't have to be an integer. So it was, and then this constant when s equals 1, h is 1/2, this is given by e squared minus 5 over 4 pi. So this was known in number theory, and then, but on the other hand, this quantity was not known in random matrix theory in 2001. So somehow this number theory computation gave a conjecture in random matrices for s equals 1 and h equals 1/2, and actually this was proven in 2011 or 12, and I'm gonna say a bit more about the history in a moment. So it's quite striking somehow that this, it's highly unlikely that this would be just a complete coincidence. It's not, it's not a number that comes up everywhere, e squared minus 5 over 4 pi. Okay, so let me leave this behind and let me tell you a bit more about the history. So, yeah, something I forgot to mention is that somehow we have, okay, let me just go back. So we have, there are like 3 distinguished cases. So h equals 0 is just the regular moments. H equals s is just we have the moment of the derivative, and s equals 0 is the moment of the logarithmic derivative. And h equals 0 is very well known, as I will explain, and completely explicit. But also s equals 0 is actually very, very simple. But this was not, it was kind of more recent result. It's not so immediate to see, but it's s equals 0 is actually the simplest case. Okay, so let me go back to the history. So for h equals 0 and s bigger than minus 1/2, this was proven by Keating and Snaith. So this is fn as 0 is really completely explicit. It's just the Selberg integral after some, just do some, change of variables. You get the standard Selberg integral, and then that's known to be given in terms of gamma functions, or in terms of Barnes G functions, and the asymptotics are very, very well known. So everything is super explicit for h equals 0. And I will give you the answer later. And then Hughes in his thesis, he proved this conjecture for S and H in positive integers, and he used asymptotics for topless determinants. And the expression for FSH also made sense for non-integer S, but the proof was, the steps in the proof, they needed S to be an integer. So then Connery, Rubinstein, and Snaith gave an alternative proof when S and H, they're equal, and they're integers, and they obtain a different expression for this. And then I think same year or soon afterwards, Forrest and Whitty connected this this leading order coefficient when S and H are equal and they're integers to Painleve equations. Okay, so then in 2008, De Hey gave a proof of the conjecture again for S and H integers using symmetric functions, and the expression again made sense for non-integer S. And Wynne in 2012 in a very interesting paper, he proved the conjecture again for S integer and half integer H. So in particular, so he gave this as a sum over partitions. This was the expression he got. And in particular, he proved this this kind of conjecture coming from number theory, this side that f1 1/2 is e squared minus 5 over 4 pi. Okay, and then so yeah, I'm just stating this, but I will give you somehow, I will give you all the equations later and expressions that somehow generalize this in later in the talk. And then in 2000, a couple of years ago, we have 2 groups of seven authors who studies the problem again. And so this first group, they connected f and sh to Painleve equations for s and h in N and got a different expression for FSH. And then this other group extended somehow these approach. I mean, of course, they did other things as well, but they extended this approach of Convery, Rubinstein, and Snaith, and obtained essentially an analogous result as the group above. Somehow, from you know, in terms of what's of interest in this talk, and this group here, they connected this to Painleve equations for finite N as well. It's not just in the limit. Okay, so let me give you the main. I'm going to give you first main result of this first paper where we study asymptotics. So have S bigger than -1/2 and H up to this this threshold here. Afterwards, the moments don't exist. Then indeed we have this converges to some limit FSH, which is a non-trivial limit between 0 and infinity. And okay, so this exists. And I will tell you in a moment what this FSH is. Oh yeah, I'll give you some history. I mean, where it's coming from. Somehow, let me just tell you the main thing is that this thing you can write it in terms of a moment, the moments of a single, of a real valued random variable somehow. But this random variable is kind of weird. So instead of just giving you this random variable, I will just tell you first the history, how it appears. I mean, it appears somewhere else. So I'll explain that and then come back to this. And then the main point is that we have this probabilistic representation for this in terms of that random variable, and then we try to study as much as possible this random variable. Okay, so to give you the history, I have to take a small detour. So this is, you know, this slide is a bit, you know, it's kind of abstract and yeah, not too precise, but it's just to kind of organize our thoughts. It's not so important. I'll give you concrete examples in a second. So you have this chain of compact groups, G1, G2, blah, blah, blah. And then I'm considering G infinity, which is the inductive limit of these compact groups. And this is acting. And then we have some Polish space X in the background, and this big group is acting on this space. Somehow I will give you very concrete examples in a moment. And then our goal is to classify the ergodic measures for this action. So ergodic measures are the probability measures that are invariant under this action, so that the invariant sets have measured 0 or 1. And in this specific setting we have this inductively compact group, G infinity, then this is equivalent to the classification of extreme or decomposable invariant probability measures. So we have probability measure which is invariant under this action, probability measure zone X, which is invariant under this action here, and if I can write it in this way, then necessarily all three are the same. So this is equivalent. Like these are the extremal measures, and actually they're equivalent to ergodic measures. And let me give you two very simple examples before giving you kind of the example of interest where this random variable first came up. So okay, I guess maybe the simplest possible example is this Definitis theorem. So now we have these groups are just the symmetric groups, and X is this space of binary sequences, and I'm just this G infinity is acting by permuting the coordinates. And then the Definitis theorem tells us that the ergodic measures are essentially these IID Bernoulli measures. So they're parameterized by have a parameter which takes values between 0 and 1. So the space of ergodic measures is parameterized by this single parameter, 0 and 1. And okay, so a more advanced example is when we have the unitary groups, and now they're acting or C to the n. So and the action is by multiplication, and the ergodic measures are simply the IID complex Gaussian random variables, and then here we have some, again, a parameter which is giving us the variance. Okay, so let me give you the more advanced example that I'm interested in, and now we're gonna have infinitely many parameters. So okay, so this more advanced example. So we have unitary groups, and now they're acting instead on the space of infinite Hermitian matrices. So you have Hermitian matrices, and oh, by the way, this U infinity basically is just so it's an infinite matrix. You have in the corner we have just some unitary matrix from UN for some n, and then the rest is just it's just the identity. And then this thing is acting on Hermitian matrices. And now we're interested on probability measures on infinite Hermitian matrices, which are invariant by this action on H of U infinity on H by conjugation leaves those probability measures invariant. Okay, and okay, I mean, I'm giving here this infinite dimensional space omega, which is going to parameterize those, but I will give you the precise statement in a minute. I mean, you don't have to remember, you don't have to remember details, just we have infinitely many parameters. We have this parameter alpha plus, parameter alpha minus, parameter gamma 1, and delta. And delta is more convenient to consider parameter gamma 2, which is given as delta minus these alpha parameters. So somehow we have two infinite sequences of parameters. These are ordered, and then we have two kind of extra parameters, gamma 1 and gamma 2. And then the ergodic measures on infinite Hermitian matrices invariant under this action by conjugation will be parameterized by this omega. So let me give you the statement. Okay, so this is a theorem by Pickrell and Olshansky and Vershik from. So okay, I'm going to tell you in a moment something about the proof, but so we have these ergodic measures on H, which are invariant under that action. They're bijection with this space omega. And then an ergodic measure on H is determined through its Fourier transform as follows. So we take the Fourier transform, so you're testing this against some kind of diagonal matrix, R1 or 2 Rn. And then, so this H is random. And then this is given as explicit, and it's given as a product from, depending on how many diagonal elements you have here, j equals 1 up to n of this function R omega. So where this little omega is in this big omega, and then this has this explicit expression here. Okay, I'll say something more concrete in a second, but before let me just say something about the proof. So somehow Pickrell, what he does is he proves that this kind of classification is equivalent to the classification of totally positive functions, which was known already from the 40s or 50s. Yeah, 40s or 50s. And then Olshansky and Vershik, I mean, they have a very different proof, which somehow kind of explains where this these parameters come from somehow from these random matrices. And essentially these things are asymptotic eigenvalues, these things are asymptotic trace, this thing is related to asymptotic sum of squares of eigenvalues. And yeah, their approach is very important in what follows. But let me say something more concrete. So yeah, I mean the characteristic function has this product structure. So basically this n omega is the law of a random matrix, and this random matrix is just the sum of independent infinite random matrices. So we have gamma 1 times the identity matrix, so there's nothing random here. Then we have G2, which is some GUE matrix with variance gamma 2. So you have this Gaussian component. So gamma 1 is the identity component, gamma 2 is the Gaussian component. And then we have some sort of degenerate Laguerre ensemble matrices here. So these are, all of them are, they're independent. So these are infinite row vectors. So here I get a matrix. And then so I get an infinite matrix here, and then I have these parameters, the alpha pluses and then the alpha minuses. So yeah, it's a concrete description. That's all I'm trying to say here. Okay. So and then once you have this classification, then Brody and Olshansky proved the following: that if you take any probability measure on H, which is invariant, but it doesn't have to be an ergodic measure, an extremal measure. Just take any measure which is invariant under that action on H. Then there exists a unique probability measure on omega, which somehow explains how this measure decomposes into ergodic components and ergodic measures. So this is some kind of Shoke type theorem, if you like. So this explains how, yeah, I mean, how does this decompose on the extremal probability measures? And so this is an abstract theorem. It tells you this mu exists and it's unique and it's defined through this. But and somehow a natural direction of research is to, you know, if you have a measure here m, which is interesting and which is distinguished for some reason, then you want to understand how this decomposes into ergodic measures. So you want to understand this probability measure on omega. And so in particular, what you want to understand, so you want to understand these random parameters now. I mean, under this probability measure, these alphas, the pluses, alpha minuses, gamma 1, gamma 2, just these random parameters, and you want to understand their law. And somehow, okay, I mean, so in most cases, I mean, because this kind of problems that we study a lot, this sort of parameter gamma 1 is the hardest to study. Okay, so let me give you a distinguished probability measures on H. So we have, okay, so these are s bigger than -1/2. I'm defining them, this probability measures as follows. They depend on this parameter s. This is n times n Hermitian matrices. And okay, so this is, so there's some normalization constant, so that's probability measure. If s needs to be bigger than -1/2, otherwise you cannot normalize it. And then if you like is, so for example, for s equals 0, this is essentially it's the random matrix analog of the Cauchy random variable. And then when n equals 1 and s is general, this is something that's called the Pearson distribution. So this is, and sometimes it's the random matrix analog of these random variables. And okay, so this really, they were introduced by Hua in a book where he studied these probability measures, and he computed some matrix integrals. And there's a very long history of works. But the main thing that is of interest to us here is that okay, I mean, obviously these are also unitarily invariant. Then is that you can actually define them on infinite Hermitian matrices. So they're actually consistent. So you just take the matrix with n plus 1 times n plus 1, and you just integrate out. There's the last row and the last column is somehow, you cut that thing, you get the corner, then you get back, you get the measure with n here instead of yeah, it's the same parameter s, and then somehow z drops by 1. And then by Kolmogorov's extension theorem, you can define unique probability measure on H. And then this is our kind of measure of interest. Oh yeah, I should say that this essentially, this is proven in Borodin, Olshansky, and Neretin, but somehow the computation of Hua in the book, at least for, so you can define this for, you can extend this when S is, it can be a complex number, but the computation for S real is basically in the book of Hua as well, because he computes these matrix integrals, and somehow what he does is just going from n plus 1 to n and so on, and that's how he gets somehow, if you want to do this matrix integral to get the normalization constant, just go from n to n minus 1, blah blah blah, up to n equals 1. And okay, so in this paper, Borodin Olshansky, which was somehow the main the main point of this paper was to study this new S. So what is this new S? So this measure describes the ergodic composition of this Hua measure on H. Okay. So again, this new S is probably a measure on omega. So I want to study this. You have these parameters alpha plus, alpha minus, gamma 1, and gamma 2, and you want to understand yeah, their law. And yeah, under this this probability measure. Okay, so before, yeah, just before giving you the answer, so let me just define. So we have determinant of point processor on our stars is R without zero. So it has this correlation kernel, and this is called the integral form, and you have explicit expression here of some functions. You have Bessel functions basically, but okay, you don't have to remember the formula, but it's just a correlation kernel in this integral form, and it has an explicit expression. Now, of course, yeah, I have many equivalent definitions of determinant of point process, but somehow we just write one here. So we have particle, you have distinct points, and you have particle and some infinitesimal interval around this point. You can write this probability somehow as a determinant of this thing here. So somehow all the information is given in terms of this kernel, and yeah, it has some expression which is explicit. So okay, so what did Borodin-Olshansky prove in that paper? So they proved that under this probability measure in US, if I take the alpha parameters, so these are non-negative, and then I take minus the alpha minus parameters. The alpha minus parameters were non-negative as well, but now if I take minus, they're negative. So I'm considering that as a point process, this is the same distribution as a point determinant of point process with this kernel. So under US, we have random parameters, and if you consider them as a point process, actually you can show that, with probability 1, they're distinct. So the law of these parameters alpha plus is alpha minuses under US is completely determined, and it's actually is given by the law of this random point process, which is a determinant of point process, and we know the kernel explicitly. So the alpha and the alpha minus parameters were completely understood in this paper already, and they proved that for S equals 0, which is kind of quite special, as I mentioned earlier, in S is 0 is very special. They proved that gamma 2 is 0 almost surely, but for S not equal to 0, they believed that it was still 0. But the parameter gamma 1 was not studied at all. And then around 15 years later, Hughes proved that gamma 2 is always 0, as they believe. And moreover, gamma 1 is basically the kind of principal value sum of the points of this random point process CS. So if you don't have this, so somehow you cut off the points that are too close to 0, you take the sum, and then you just remove this cutoff. So if you didn't have this, then this diverges. So you need to do this, remove the points that are too close to 0, and then yeah, that this limit exists. And this is the random variable that I care about somehow. So this kind of all this history was to tell you that there's a random variable which is given as a principal value sum of points of a determinant of point process, and this determinant of point process comes up in this problem, and also this random variable itself comes up in this problem because it's the law of this parameter gamma 1. And then this random variables appears in my thing here. So this is the theorem. So we have this limit, and this is given explicitly as f as 0. Okay, this is, as I said earlier, this is completely explicit in terms of the Barnes G function. I'm just giving you some formula here. So yeah, this was well known. And then we basically have the moments 2h moment of the absolute value of this random variable xs. okay, I mean, in principle, could have written it slightly differently. So essentially what we really want is excess over 2, but it's fine. So, okay, so basically we want to understand this leading order coefficient as much as possible. This really boils down to understanding this random variable and its moments, because this is completely explicit. I mean, you cannot go further than that. So this boils down to understanding this as much as possible. Okay, so let me. Okay, so now I'm gonna talk about. I'm gonna give you some results about the actual random variable now. Okay, so for integer, so this is general S and integer H. Oh yeah, but actually, let me just define. This is the expectation with respect to. So let me go back. So this probability measures a random matrix, as we said on Hn. It has n random eigenvalues on the real line, and let me just write expectation with respect to those eigenvalues. I mean, denoted by this. And then in this paper with John Keating and John Warren, we show that when H is an integer, so in particular just looking at these even moments that are the same, we don't need the absolute value, and any is bigger than this, so we need this, otherwise the moments will exist. Then we have the following formula, that these moments are given in terms of the moments of these finite n matrices. So these are the k eigenvalues of a k by k random Hoa-Pickrell matrix. And then with this formula, you can show that this is actually for fixed H is a rational function in S. And it's actually, well, I mean, actually quite good to compute things from like first principles. For example, it's very, very easy to show that the second moment of XS is just as this very simple formula here. So if you try to show this from the determinantal point process, I mean, I don't know how to show it directly from the definition of the determinantal point process, right? Because you have to, in principle, you get you can write things in terms of integral of the kernel, but you still, it's rather complicated because you have this kind of principal value thing, which complicates things slightly. But yeah, it's kind of amazing that you get such a simple formula in the end. But the thing is, you don't even have to use this to compute things. I mean, because the main thing is, as I mentioned earlier, this sort of thing, FSH for S integer was already computed, and it was a rational function. So if this is a rational function as well, and they match at the integers, then they're the same. So somehow this immediately extends the previous formulae, combinatorial formulae for this. It immediately extends those. But okay, I will say a bit more about explicit formulae in a second. Okay, so that's one. And again, this, okay, so this, yeah, the approach here, okay, maybe I'll say a bit more later. Okay, so now, so this connection to this and then Painleve equations. So for any s bigger than -1/2, we take the characteristic function, take the logarithmic derivative, multiply by t. And then in the same paper, there are some restrictions here. I will explain why they're here. We prove that for this s bigger than integer and bigger than 1, this satisfies in some small interval around 0 the Painleve 3 equation, which is the sigma form of the Painleve 3 prime equation. And okay, these two parameters you can somehow, yeah, can forget this for a moment. And then this is given, so we have this equation here, and then we have boundary conditions. So 0 is 0, derivative of 0 is 0. So this is, yeah, this equation. So let me say a couple of things why do we have these restrictions? I guess first of all, we have this restriction for integers because somehow we take as input the result that I mentioned earlier by the 7 this 7 author paper where the result there was proven for finite and for integers. So that's somehow where these restrictions come from. Why do, okay, so again, small interval around 0 is because it's not vanish in a small interval around 0, but you know, this characteristic function might vanish. And then this, that s needs to be bigger than 1, actually we actually do need this, because if we're looking at, because we're including 0, because around, so we need so if you look, we need three moments, so we need s to be bigger than 1. Somehow the only problematic point is around, the only problematic problem is 0, but the thing is, we use the moments here to prove things. So somehow we need to include 0 in a way to argue. I mean, if we want to connect, you know, want to connect the characteristic function and say something about it from the moments, then we need to include 0. So that's somehow why we need that this is bigger than 1. So because we need certain number of moments. Okay, so this was the result here. And then in this,
and what is the dependence on h in this? It's like somewhere in the initial
h, no, h only appears as a moment of this round. Somehow all the information is in XS. You see? So h is afterwards somehow. First I understand XS and then I do. Okay, so okay. And then in this subsequent paper, we can prove that this solves in R star. So we don't want 0. It solves the same equation. So somehow the starting point is different, as I said, and the way to prove is different. Of course, we have somehow boundary conditions. We need s to be bigger than 0 for this, because it's not continuous. It's not continuous. This thing is not continuous at 0. This thing is actually not differentiable. It's not differentiable when you know, we need s to be bigger than 0 to be differentiable, and then similarly for s bigger than 1/2 here. Okay, I should say the boundary conditions here are proven using, of course, using the moments. So this is somehow basically taken from the previous paper. This is new in the paper. And then as an immediate corollary, we get this representation like for integer h. So yeah, I mean, okay, of course we know that we can take the characteristic function, take derivatives of that, evaluate at 0, get the moments, and basically this is what this formula is all about. Somehow this is what it's saying. So this is the balanced G function I have from before, and then if you take the derivative of the characteristic function and evaluate at 0, get the moments. So this is this formula for h in S and in integer n and general a s. Okay, so this was the kind of equation connection. Okay, but then the question is, you know, I mean, if I want to say more explicit, is it possible to say more explicit things? And I'll say something more about them now. Okay, so as I mentioned earlier, for general S and integer h, there's explicit formula, which is obtained using, you know, some quite, in this paper by a very different method. And now I'm gonna say that for integer s and general h, there's also very explicit formula. So the thing is, so XS has an explicit probability density with respect to the Lebesgue measure, this XS, and for integer s, and I'll say a bit more about it in a second. And it has we get an expression for the moments, which is given. Okay, so this is some complicated combinatorial coefficient that we'll say more about it in a second. And one more thing that I should mention now is that, okay, of course this vanishes, right? I mean, when this is let's see, when does it vanish? When h is 1/2, right? When h is a half integer. So this vanishes as well, and then so this understood as you apply L'Hopital's rule. But it's actually not so clear a priori. If you look at this combinatorial formula, it's not so clear that it should vanish when h is a half integer. So okay. So somehow, yeah.
In this case, these symbols, some of the -2hk is the gamma symbol.
Yeah, it's a Polynomial symbol. Yes, yes.
And what about the CKS?
I will give you a definition in a moment. So this is the combinatorial. Yeah, can you hear me?
Yeah, you're back.
Okay, yeah, it was got a bit stuck. So yeah, so why are these so why is that integer s special? So somehow the corresponding functions are solutions to this sigma form of this Painleve 3 equation, and they're actually what's called classical solutions. So this is not classical solution in the sense of PDEs, is classical in a different sense. So these are classical functions, which, I mean, the definition of which is yeah, I mean, there's a very how should I say, it's very precise but very technical definition I cannot give you now. But let me just say informally what a classical function means. And in this setting, essentially, it means that you can write it in terms of you know, special functions that are known in some sense, that are classical special functions that people knew in the, just saying, the 1900s, like things like Bessel functions, hypergeometric functions, and by in terms, I mean, you can, of course, you can take sums, products, can differentiate, you can integrate, can also solve linear differential equations with those as coefficients and so on. And so there's some set of operations that's what I mean by in terms of those. And okay, I will tell you in a moment how yeah, you know, in terms of what you can write this psi s. So, but let me first give you this combinatorial coefficient. Okay, whoops. Okay, so this combinatorial coefficient. So we have, can write it as a sum. So we have this form here. So we have some determinant, we have some factorials, or you can write it in terms of, again, it's a combinatorial sum, which is very similar. So as you say, these equalities are really they're kind of trivial, because it's just somehow this, you go from conjugate partition to, you know, go from partition to a conjugate partition. And that's how you get this. I mean, the main thing is this one, but also this is, yeah, so this is a generalized Polynomial symbol associated to partition, and then this is a hook length. And then if you, yeah, okay, so if you're familiar with these things, you can see it has a very similar structure, actually. This is two formulae, but you need to some elementary combinatorial computations to actually show they're the same. So in the paper, we only use this one, and I will explain where, I mean, so you can show this equality directly, but somehow these two different expressions they come from equivalent expressions for a density for the characteristic function. So one expression for the characteristic function is in terms of Bessel functions, which is the one we use in the paper, and another expression for the characteristic function is in terms of hypergeometric functions, and this gives this one. And then you can also show directly, as I said, some combinatorics can show that these are actually the same thing. Yeah, okay, so somehow this case s equals 0 is like extremely special, as I will explain in a moment. But also cases s equals 1 and s equals 2 are very special, because you can actually compute this sum, and you're only left with you know, you can compute it, and then you kind of only left with some single sum, and then you can write s equals 1. You can write it in terms of the 1f1 hypergeometric function, and for s equals 2 in terms of the 2f2 hypergeometric function. Okay, So let's just see s equals 0. So yeah, s equals 0 is so s equals 0 is special. So x0 is actually Cauchy random variable. Yeah, it's extremely simple. But what's kind of crazy is that it's not that in the limit we get that this x0 is Cauchy and the leading order coefficient is nice. It's actually the joint moments are always explicit and they're always super simple. Just given by this thing. This is just the moments of the Cauchy random variable. So just for all n, this is exactly equal. And actually, it's not so, yeah, it's not so trivial to see. I mean, somehow the main reason the way you can see it is, so if you write down the characteristic function at, okay, maybe I should explain this a bit later. But somehow there's a non-trivial transformation that allows you to see somehow this immediately. And this was somewhere, it was already, this transformation was already in this paper by Wynne, but it wasn't, there it was used as an intermediate result. It wasn't kind of seen as the characteristic function of something. So that's probably why it was missed, that is just Cauchy random variable and somehow everything is known. Okay, so let's see. So, okay, so I have some ideas about the proof. Okay, so yeah, so I guess the main, the starting point, the key observation is that after some transformation, you can write as Fn sh. So the joint moments, you can write them in terms of the standard moments without h is 0. And then as the trace of this, the moments of the trace, the key, key starting point, key identity. It's not too difficult to show, but somehow the main thing is to realize that this actually, this is actually useful. And then by the general results, I'll explain in a moment. So this is Borodino-Olshansky, and combination of this result of Borodino-Olshansky and Hsu, you can show that this thing you divide and then you get this random variable. So the result of Borodino-Olshansky says, which is somehow it's much more general. It holds for any this unitary invariant measures, not just for pickerel, and in fact you can generalize it to kind of beta ensembles. It's that normalized trace converges, so that's kind of a general result. And then the difficult part is showing that actually, it converges some random variable, but Hsu identified this random variable in terms of this kind of principal I use them. So what we do, so we divide things here is kind of elementary. You see, what we want is to show that the uniform integrability of these random variables. Okay, so you might think, well, everything is kind of known almost, so it must be somehow these are determinantal, so it should be easy, but somehow it's a bit trickier. So this is a determinanta point process. This is super standard, and then the kernel is given in terms of this pseudo-Jacobi polynomials. Okay, and then so then we know that the extremal points grow linearly in n. So somehow for the sum to converge, there's a cancellation because of symmetry at 0. Somehow the positive and the negative parts, they cancel out, and that's the reason this thing converges, because otherwise these things are of let's see, so these are grow linearly somehow in n, so you get some extra power. I mean, in fact, you can show if you just take naively absolute values inside this, you get some grows like log n or something like that. So it doesn't converge. So you have to take the cancellation into account. And then you want to estimate this. So this is the sum of points of determinanta point processes. And then we want to estimate it uniformly in n, but we want to take the cancellation into account. Somehow, if you don't care about the cancellation, then it's kind of easy, because you can use Hadamard's inequality, and then it will boil down to an estimate of the kernel, the diagonal. So it's going to be an estimate of KNSXX. And that's, you can use estimates for the polynomials, and you can do that. But you want to take the cancellation into account. So it is trickier. And it's possible to make it work to some extent, because somehow we cannot access all this full range of H values. You can only go up to some integer. So you can only do, you can get a bound for some integer H, and then you can somehow do the rest H, which is less than that. So you cannot go up to S plus 1/2 in principle. I mean, at least in this way. Well, and then the next key idea is that, okay, I mean, instead of studying, so this determinant point process is really nice, but on the other hand, there's also eigenvalues of a matrix. So sum of eigenvalues is sum of the diagonal entries. And the diagonal entries are, yeah, really, really good. I mean, they're not so good for computations. They're not so good for, you know, computing things like determinant point process, but actually very good for, you know, proving things converge and getting estimates. They're much better. So the diagonal elements of this matrix. So first of all, you know, you can couple them because I have this infinite matrix, and then they're exchangeable. So it's so you get the bound that they're uniformly integrable. You get this for s bigger than 0, which means we have these are in a 1. You get this, basically you get this immediately. And it's okay. So in this L1 regime, we have the law of large numbers for exchangeable sequences. So in principle, we can use this. So you can use this independently. You don't have to use the fact that this converges. You can get it, yeah, you can prove it in a different way anyway. But when you don't have one moment, then the situation is a bit more subtle. And okay, the main idea, these are exchangeable. So if they're exchangeable, so conditionally on what's called I forgot the name. So it's like it's Theo, I think, yeah, it's a Theo sigma algebra. They're IID. They're IID with eminent variance, which you can connect back to these things. There's XS and CS, and then you can analyze them. You can use some determinant point process, you know, theories, and then you can do that to cover this as well. But for S big, it's good to use the diagonal elements. It's pretty immediate. And then here, okay, I'll come back to these when I just say something about open problems at the very end. So somehow, because these things work for somehow beta ensembles as well, but this thing don't exist for beta ensemble. Okay, and then what about this other paper? So yeah, Painleve representation approximation from finite end. So that's how we prove all this result. So the starting point is, instead of using the formula that was used in the 7 author paper, use a characteristic function. You can write as a Hankel determinant of a Laguerre weight, which is as a deformed Laguerre weight. And then this is Hankel determinant, and there are actually many different methods to show that this is gives you, I mean, this particular one, it gives you a Painleve equation. And then if you take the limit as n goes to infinity, you get this Painleve 3 equation. But the main thing, somehow, you don't want to use the moments, because then you necessarily gonna have the restriction as bigger than 1. So that's and also you can remove the restriction that this is solved in some interval, because you can show the characteristic function doesn't vanish anywhere using, again, using this formula. This is somehow a better formula for doing this. And also, it's kind of interesting. Somehow, if you want to study characteristic function, it's not a good idea to use the moments. And also, if you want to study kind of just the moments, like conversion of the moments, it's not so good idea to study the characteristic function. And then for integer, as I mentioned, so finite end, the characteristic function is given in terms of determinant of Laguerre polynomials, which is what we use in the paper. Also, matrix hypergeometric function. And then actually, this is used in a recent paper by Peter Forrester. I mean, he uses the representation in terms of matrix hypergeometric function, which also makes sense for beta ensembles. But again, S has to be an integer somehow. It's yeah, I didn't mention earlier, but yeah, S is really special in the sense, because for non-integer S, then accept some solutions which are not the solutions we want, that equation has this non-classical solutions. So somehow, okay, maybe you can write it in terms of you can write an explicit expression, but you cannot write it in terms of this kind of known special functions. So yeah, we use this in Laguerre polynomials, but also now in the literature exists, you can use the hypergeometric function. And then in the limit, you get Bessel function, again, this series, some combinatorial coefficients. So somehow, this is the way these two different types of coefficients come up. And then you have to prove some things converge, of course, but then this is kind of standard of, you integrate all these things and you can get the moments. Okay, so let me finish with some open moments. So yeah, I guess the main question I've been thinking about, so yeah, it's not so clear. I don't know what the answer is. So as I said, we have explicit expression for general S, integer H, and integer S, general H. And then my question is there explicit evaluation of this thing for general real S and H? And basically, you should also boil down to, do have explicit expression for solutions that are not these classical solutions of the Painleve equation. I don't know. I mean, I think there are some things in the literature where people study, they have asymptotic expansions and so on, which are actually, they're much more complicated things than the expressions that I showed you, which are anyway kind of complicated. But it's not, we thought about that, but it's not so, it doesn't look like it's the thing we need, or it doesn't seem like it's something in our case, but maybe it's possible to have explicit expression for general S and H. So what happens for
about the asymptotics, like of this when n is large, or when so you want the asymptotic expression. So you have the formula for integer H and general S, right?
Yes.
And do you have so there is no explicit formulas for this integral, right? So you have like integral of Painleve function, and then you have H derivative of that, and you want some.
You mean somehow? What's not explicit is this somehow? This is not known explicitly in general.
So in this formula, yes. So this corollary, it's not explicit enough. The same.
But in this case, this corollary, this much is essentially it's explicit because it is the same as this formula somehow. But okay, that's a good question. It's not so clear how, because this is general S, so it's not clear how this formula, because it's for general S, how we could independently prove from the Painleve formula and this explicit formula here. It's kind of directly. It's not clear.
So are there any combinatorial expressions for?
The combinatorial expressions are
for this corollary for integer H and non-integer S.
Yes, for this one, the combinatorial expression exists for integer H and non-integer S. So we have one combinatorial expression here, but you can, as I said, you can write a fully explicit combinatorial expression. This thing can be evaluated, and but also there's a combinatorial formula also for integer S and non-integer. So somehow, if one of the two parameters is integer, a combinatorial formula exists. But the question is, does there exist some combinatorial formula when both? I mean, let's just say S is 1/2, H is 1/2. Is there some formula for it? I really don't know. So it's really not so clear. Also, of course, I'm not an expert in this Painleve equations, but I mean, I kind of looked, and it seems to me that not so much is no, in terms of explicit expressions for these non-classical solutions, it's not so clear. I mean, how much?
But you say that you have some combinatorial expressions, or they're not good enough, or
Well, we have them for S integer or H integer.
yeah, but for if H is not integer, you don't
And
have Painleve, right? Like you don't have any expressions for non if both of them non-integer.
well, when H is non-integer, we have expressions when S is integer.
Yes, yes, but so the question is not about Painleve, right? Or
Yeah, the question is not somehow, the question is, well, somehow the way we get this expression for integer S is because the solution is known to be completely explicit. Somehow, if we knew the solution is completely explicit for non-integer S, we could just again integrate, do all these things and get the expression. But
so you're saying that this expression for integer H and non-integer S, it's not good enough. So you don't have you need for non-classical Painleve 3 equations, you need better knowledge about it or something.
yeah, I mean, somehow we want for non-integer, yeah, we want an explicit. So somehow for when S is an integer, this is as a, I can write the solution down in terms of Bessel functions. But I mean, if S is 1/2, I don't know. I mean, I don't know what can be said somehow. Somehow you can say you can write down such a formula, but it's always in terms of solution fund, but somehow it stops there. I cannot write it down. That's my, you see what I'm saying? So somehow for S equals 1/2.
But what about this other formula in terms of expectation of this sum?
Yeah, I'm okay. I mean, this obtain is a completely different way, and it's my more probabilistic way. So it's really, yeah, it's really unclear. I mean, also this is very essential that H is an integer here.
Well, H is integer there too, right? It's derivative. So
well, yes. So somehow this formula and this formula that you can, yeah, they're equal. But I'm saying, but here H doesn't have to be an integer when S is an integer. Somehow, so that's my, so I mean, okay, what I was thinking is whether this kind of result can be extended to non-integer S, but I'm saying this result is very specific because it's very specific that I have these special solutions in a way. You see?
yes.
Okay. So, oops, okay. And then C beta E, as I said, kind of the arguments of the first paper, you know, the convergence argument works as well. It has a kind of similar, you have very similar structure, at least when you have one moment. But this identification with the limit of excess, like this is not known. Somehow the statement ends with, you know, the limit exists, there exists some random variable so that you're looking at its moments. But there should be some analog of this. So somehow you have principal value sum of the kind of a beta version of this point process. And as I said, for S integer, this is now in this paper by Peter Forrester, you can compute things for S integer because you have this hypergeometric function representation. But this is when S is not an integer. So for example, it's not clear whether there's this connection with integrable systems or it's just special for beta equals 2. And then the other thing is, you know, alternative proof of the Painleve representation, just we have determinant point process. So we have a Fredholm determinant. Okay, of course, this is principal value sum, so you have to take some limit, but somehow, you know, the alternative proof is, you know, prove directly that this solves Painleve equation from the determinanto, you know, using Fredholm determinants. So that's should be possible, but yeah, I don't know. But also there's a simpler problem where you're looking in terms of principal value sum of this point process, you look at Bessel process and you take sum of 1 over points of Bessel process, and then that solves a different Painleve 3 equation. And in that case, there's no principal value sum, there's nothing like that. So it should be even simpler, but that also, yeah, that's also not known. And then, okay, extend the result to negative H. So this would probably require a slightly different argument, or you can, when H is small, you can go beyond S minus 1/2. But then these Hoapicron measures are no longer normalizable. There's this called infinite Hoapicron measures, and there's a lot of theory for them as well. And probably you can do similar things in that setting, but yeah, it's gonna be kind of significantly more complicated, I suppose. Okay, so that's it. Thanks. Okay.
Thank you. So, so let's see if somebody has some question. Otherwise, I have a question for about one of the points that you discussed in the last slide. So for general beta ensemble, okay, you said that there is no generalization of this Hoapicron measure.
There is.
Ah, okay. So I did not. So in that case.
Yeah.
So for
Okay.
general beta, what is the generalization?
So what's the generalization of so it's just the beta ensemble. So okay, so you don't have a matrix model, but you can write down that in terms of the. So what we care about are the eigenvalues, right? So we have so instead of the van der Waals square, you have van der Waals to the to the power beta, and then with this weight. So we have some kind of weight. One is one-dimensional weight, and then van der Waals determinant to 2 beta or beta, and an analog. So this kind of formula will where is it? So this formula here will exist. So somehow, so this you're gonna have a beta here as well, beta, and then you're gonna have beta ensemble Hoapicron eigenvalues. So you get this. So this exists as well, and and then the main question is, what is the analog of the diagonal elements, right? Because we have no matrix, but you can do this kind of interlacing array consistent measures, and the diagonal elements, you can get them from the interlacing array. So it kind of, the picture exists, you just don't have the, we don't have the kind of, yeah, I don't have the matrix, but the diagonal elements, these things exist. Okay, this thing don't exist, so the argument here needs determinantal, so you cannot get it in this range. But when s is bigger than 0, the argument works. And but somehow this is not known. This is somehow this. What's the analog? You see, the analog of this should be some kind of principal value sum of the beta ensemble point process for Hoapicron, and that's not so it's not known. And that's probably difficult to prove it. I mean, just, yeah. And then also Painleve, somehow integrable system connection for beta ensembles. I mean, for gap probabilities and all these things, I mean, I think some connections exist. I'm not so familiar, and I guess I'm wondering whether maybe something similar will exist in this case. But again, it's probably, yeah, much more complicated.
Okay, let's see if somebody else has some question.
Yes, I have a question, if I can. So at the beginning of the talk, you were talking about the relation to the Riemann zeta function and the unitary ensembles, and then you switched to this Hoapicron measure, determinant of 1 plus h squared. And is the connection there because, I mean, from what I could tell, it's because you just picked it because it was interesting. But is there a connection there? Because I understand that circular ensembles and the Hoapicron measure are connected in some way.
Yeah, somehow the connection to Hoapicron is essentially because somehow the zeta function and this number theory random matrix connection is between the zeta function and unitary matrices. And then the connection to Hoapicron, I mean, it's just because unitary, random unitary matrices are connected to Hoapicron, right? I mean, I don't know if it's any kind of direct connection between this, this number theoretic functions to these ensembles to Hermitian ensembles. So basically, the connection is to the random unitary matrices, and then because those are connected to Hopi-Kroll, that somehow you get this connection in a way.
Right, yes. I was just trying to guess your motivation for looking at the Hopi-Kroll measure.
No,
Or
yes.
how the two halves of the talk are connected.
Well, somehow, yes. Somehow the motivation is this formula here, that I have the joint moments, which is the thing I care about at the beginning. And I can write it in terms of the moments of the trace of the Hopi-Kroll measure. Do you see? So this is the thing I care about at the beginning. And then I can write it in terms of Hopi-Kroll measures. So that's why I'm studying this in a way.
Yep,
so
that makes sense. Thanks.
So
Well, okay.
are there any, sorry, are there determinantal representation for moments of XS?
Somehow, well, moments of excess, so you can write so yeah, you can always write, so you have a sum of moments, so the sum of points of a determinanta point with sum of points of a determinanta point process. You take the moments, you can expand that in terms of the integrals of the correlation kernel. But in this case, there's some extra complication because this is kind of principal value sum. So somehow it's a good question. It seems that from the determinantal definition, it's hard to compute things somehow. For example, even this thing, I mean, I don't know. I mean, I guess this is probably the simplest possible thing like you try to compute. I mean, the answer is very simple, but it's not so simple. I mean, I haven't tried. Yeah, I haven't really tried. I mean, I wrote it down, but I couldn't really see. And it seems to me probably might need to some tricks. It's not so clear if there's some real problem or it's just you have to, do a lot of computation until you see something as simple as this.
Is it easy to see that it is rational function?
Directly, I cannot see it, but you can see it from here because here you can show that this is a rational function, this integral. So it's again a computation, but exactly, yeah, without this formula, it's not so clear because as you see where S is coming. It's coming here, it comes here as well in the Bessel function index. It's not, yeah, it's not so clear somehow, right? Well, actually, it's not clear at all to me. I mean, yeah, but yeah, maybe it's possible to see it, but somehow I guess the easiest thing possible if somebody if it's possible to do a computation like this, and then of course this computation will be very interesting, but still it kind of use Fredholm determinant to study, show that it solves differential equation. But still, it's not a trivial thing, I think. So.
Well, okay, maybe there are no further questions. So let's